In this 6.4 section, everything is focused on identifying rational and irrational um, numbers. And so let's talk about that. Rational numbers can be written as fractions. Okay, so a rational number is something like 2 ninths. Totally irrational number. If any fraction you can dream up, 51 over 80 is a rational number. As long as you have a fraction, it can be written as a fraction. It doesn't even have to be a proper fraction, right? Like 4/3 or 41/5. All of those are rational numbers, and we immediately are able to tell that because they're fractions. Now, we saw some stuff last time in the last section, 6.3, like 0.35. That's rational. Remember, we wrote that as 35 hundredths. So if you can write it as a fraction, it's rational. We were getting representations of repeating things as fractions. So as if a decimal terminates or repeats, it's rational. Now, what are irrational numbers? Irrational numbers, right? Irrational, then by default, cannot be written as a fraction. Right? Other things we can say, they're decimals go on forever, right? They don't terminate like they did with 0.35 and never have a repeating pattern, right? So even down the road, they won't have a repeating pattern, because if they did, we can do the work that we were doing at the end of 6.3 in order to come up with their fraction representations. So let me give you some examples of known irrational numbers, numbers that you know. Pi. Pi, that number that we use in a circle, um, and is 3.14, and there's like posters of it. Let me just see if I can bring up pi on my calculator. I should be here, but I'm not seeing it. I see it now. Okay, sorry for the hesitation. If I type in pi and hit equals, 3.14159265359, and if you were to continue writing that, pi never has a repeating pattern at all. Another one is the square root of 2. Pretty much any square root that you have to leave on because you can't simplify it is irrational. And I shouldn't say pretty much, all square roots that you can't do. So this is 237, and goes on forever, and nothing gets repeated. So things like the square root of 5 are going to be irrational, right? Or any makeup of those. Sometimes you see like numbers built like 2 plus root 5 over 3. Still irrational because of this guy. If you were to look at its decimal, you couldn't represent that number any better than what you have here. And so they're going to have you look at some things, and some things are going to be really quick. Like the first question is 7/13 rational or irrational? And hopefully it's defined well enough where you're able to say, you know what, that's rational. I don't even need to bat an eye at that. It's written as a fraction. Of course it's a fraction. What about something like this? The square root of 16. So some might say irrational, because Jensen told me whenever you have a square root, it's irrational. Careful. Whenever you have a square root that doesn't work out perfectly, it is irrational. Square root of 16 works out to be 4, and therefore it's rational. All your whole numbers are rational because they can be written as 4 over 1. Right? In this case, 4 over 1, or that number over 1. So be careful. They're going to put out some square roots and other things. So if they did the square root of 5, you should say irrational. even something like the square root of 12 that reduces, you may know, to 2 root 3. It's still irrational because of that root 3 that's with it. It's got to work out perfectly like it did with 4. What about something like 1.405? Well, this decimal terminates, so it's rational. We could absolutely write it that as a fraction. Remember, this is 1 in 405 thousandths. So absolutely it's rational. And so a lot of these are going to be just quick answers. What about 0.678? Rational or irrational? Well, apologize, it has a line over it. How about now? 678 goes on forever, right? 0.678, 678, 678, dot, 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 dot. We found out that that was rational. So if it repeats, let me come right back up to here. If it repeats, it's rational. And so it's nice and rational. E. You may not be familiar with the number E. E is what they call the natural number because it's observed in nature. It's actually the base for a lot of exponential growth problems in nature and decay problems as well. So E would be on your calculator because it's used a lot. And E is 2.718281828, and you think you have it, but then they throw in a 4-6, and there is no repeating pattern. E is like pi. It's irrational. So then that's what's happening. They're just giving you a bunch of numbers. They throw in what I referred to earlier. 6 plus square root of 2 all over 5. Rational or irrational? It's irrational. Not because of this root 2, right? Yes, it's in a fraction form, but the root 2 prevents us from writing the whole thing as a single whole number over whole number. And so anytime there's a square root in there, that comes through. So they are asking you to simplify roots. I don't know if you remember how to do that. So the square root of 24, they want us to simplify. So they're going to ask us to simplify some roots. I would recommend prime factorizing if it hasn't been a while. If you have another way to do this, please do it that way. So prime factorize, and then what a square root is looking for is pairs. I got a pair of 2's right here, so I can pull one out. And then I don't have any more pairs, so the 2 times 3 stay in. So this is 2 root 6. Essentially what's happening is you're recognizing that this is 4 times 6. Square root of 4 times the square root of 6. Square root of 4 is 2. 6. Okay. And then they'll ask you for the decimal approximation. Just drop root 24 into your calculator. So this is about the 10th problem. And so the first 10 is this irrational or not? The next few are giving you big square roots, sometimes always square roots, but square root of 288. Let's just prime factorize it. 2, 144. Do you happen to know what 144 is? That's 12 times 12. If you know that, then you can be done right away and say, oh, I'm going to have a pair of 12, so 1 can come out, but I'm going to be left with a 2 underneath. If you didn't see that, what would it look like? Or even if you did and you're like, well, Jensen said I had to prime factorize. First of all, it doesn't matter how you factor these, by the way. So it could be 2 and 72, 2 and 36, 2 and 18, 2 and 9, 3 and 3. No problem, right? And so for this 2, 1, 2 can come out. For this pair of 2's, 1, 2 can come out. For this pair of 3's, 1, 3 can come out. And we got a lone 2 that has nobody to pair up with. What's 2 times 2 times 3? Oh, that's 12 root 2. And so they're going to have you over, let's see how many problems there are. There's, looks like 3 like that. Then they're going to remind you, ideally, an Algebra 2 concept that's very important moving forward. We have this rule that says you cannot have a square root on the bottom. And so the way that we get rid of the square root that's around the 2 and still have an equivalent fraction, well, it has to be through multiplication. And what you multiply is by the exact same square root. And let's show you why. 9 times the square root of 2 is 9 times the square root of 2. There's no way to rewrite that. Root 2 times root 2. Let me write that down here, right? Root 2 times root 2. Actually, let me put it like that. That looks a little bit better. Is root 2 times 2, which is root 4, which is 2. And so this is a 2. So a square root times itself removes the square root. There's nothing special about that. Root 5 times root 5 is going to be 5. You can step through the 25 window to get there, but we don't want you to continually do that, because if we have root 18 times root 18, we don't want you to figure out what 18 times 18 is. We just want you to know, oh, the square root's going to drop because I got 2 of them. And so they're going to ask you to simplify some things. They have this problem. They have a fraction under there, 7/4. Well, we can't have a square root of fraction, so the way we handle that is we split up that square root. And then we simplify what we can. Root 7, square root of 4 is 2. So we have this irrational number, root 7 over 2. And then they want to know the approximate value. Just drop that into your calculator to get the decimal representation. Make sure you're rounding to where they say that you need to. So what if we had something that didn't have a nice bottom like that? Well, we still do the same thing, and now we're stuck rationalizing the denominator by multiplying top and bottom by the exact same thing. And we're finished. Root 70 over 7 would be there. Now, I keep mentioning it. They say, hey, write that as what is the decimal approximation? And so they want me to go out to 4 decimal places here. So I could do the square root. Let me turn my calculator back on, sorry. Square root of 70 divided by 7. And it will give me a decimal approximation that looks like this, 1.95228. And they wanted me to go to 4 decimal places. And so, well, I'm missing a 1, 1.195228. And so we're going to round right to here. And so because that's a 2, we're going to leave that and have 1.1952 as our answer. And so that takes us through about the next 5 problems. And then the last ones, the last 3, are combining radicals. So radicals are like variables. Unless they look exactly like, you can't add them. So here I have 5 root 6's, and I need to add 2 more root 6's. Of course, what I have is 7 root 6's. You just add those outside numbers. So then they have 7 root 2's minus root 2. Well, if I have 7 root 2's and I take away one of them, I end up with 6 root 2's. And so it's that nice. Now, what do you do if we're in the last few problems and they have, last 2 problems really, and they have something like this? Those don't go together at all. Potentially. We need to check. We need to make sure that all of our roots have been reduced. So if I go back up to my top ones here, root 6 can't reduce because it's a single 2 times a 3. There's no pairs. Root 2 doesn't even factor. How about the 20? 20 is 4 times 5. 4 is 2 times 2. So I can pull out a 2. So I got to be really careful. Here's the original 2 that was there. And then I'm simplifying root 20 to be 2 root 5. For these pairs of 2's, 1 can come out and the 5 stays underneath. Will you see that okay? This is the 2 that was already there. Don't forget about that 2 or blend it together. So what do we have? We have 4 root 5 plus 12 root 5's, right? This guy just comes down. And what do we have? 16 of these root 5's. So there will start us out in the last 2 on your 19 and 20 with square roots that need some reduction first. And so this is just an exercise in dealing with some square roots and also rational versus irrational numbers, which fits in there well. And so that will help round out our semester, and you'll see these on the exam and on the final. So hopefully it goes well. But if it's not going well, reach out to me through email, come to Zooms. Any way that I can be of service, let me know.